So today, I thought I'd talk a little bit about what's called particle physics, and more specifically, the standard model of particle physics. Now, the standard model of particle physics is sort of the gateway into, I call it the gateway into quantum mechanics and quantum physics, which by all means is some of the most complicated stuff of all time. Like, oh my gosh, nothing makes sense. Not even Richard Feynman, famous quote, if you think you can explain or know about quantum mechanics, you don't. It's very complicated, but something that's less complicated is the standard model. Now, the standard model is, in a way, just sort of a list of, or really it's just a chart, kind of like the periodic table, but for particles, fundamental particles. Fundamental particles being the particles where if you can't break them down into any smaller particles. For instance, you can break atoms down into protons and neutrons and electrons. You can break protons and neutrons down into quarks, which we'll talk about. But these, particles, you can't break down any further, at least as far as we know of. String theory, perhaps they are just strings or something else. But basically, quantum physics, quantum mechanics is actually the the best, most efficient, most consistently accurate model or model of our universe as of yet. It always seems to work. But particle physics is basically the idea of what CERN does. CERN, Large Hadron Collider. They are, looking at these particles. So the particles are split up into three groups: the quarks, the leptons, and the bosons. The quarks come in what we call flavors. There are 6 flavors of quarks. That's the actual term for the different types. They're just called flavors because we run out of names. We have run out of viable names. Anywho, so there's first generation quarks, which have the flavors up and down. I'm not lying, that is actually their names. So the up quark and the down quark. Then we have the second generation, strange quark and charm quark. Then we have the third generation, which is the top and bottom quarks. Now, charm, top, and bottom barely exist. Like, they decay very rapidly. Almost all of these particles decay incredibly rapidly on their own. Now, quarks, by the way, cannot exist on their own. They have something called color charge, which means a quark cannot exist without another quark bound to it. For instance, you can have either a meson, or a pion, or baryon. Now, baryon are the most common types of quark bundles, I guess you would say. And they're just made up of 3 quarks. The most common baryons are the proton and the neutron. The proton made up of 2 up quarks and a down quark, and the neutron 2 down quarks and an up quark. Those obviously form the nuclei of atoms. And then you have, other types of baryons and mesons and pions and all that other stuff. But they don't exist for much longer, fractions of a second. But basically, to start off with, you have the quarks, and they are, I'll get into something down the road called matter-antimatter asymmetry, which is very, very interesting. It's something we're still trying to figure out why that happened. But anyway, then you have the leptons. And I should also point out, actually, before I say it, each particle has something called a mass, a spin, and a charge. Now, mass, everybody pretty much knows mass. Mass is pretty an intuitive property, and charge is also a pretty intuitive property. Charge is measured in fundamental particles with the electron unit, which is basically so an electron has a unit of -1 because it has a negative charge of 1 electron unit. And so almost all the quarks either have a charge of 1/2 or 2/3 positive, negative. And that's basically how it works. And then, yeah, you can get into other masses. Masses are measured in electron volts, usually mega electron volts or giga electron volts. And then you have spin. Spin is interesting because spin is, the best way we can explain it is that a particle looks different from different angles. Same thing as, if you look at just any object at different angles. Take, say, this rock, for example. If you look at it from this way, it looks different than looking at it from this, or 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 this. Looks different ways you look at it. But a particle, sometimes, so if you have a particle with a spin of 2, I call it sort of the counterintuitive method in my head, because if you have a particle with a spin of 2, particles usually have a spin of 2, 1, or 1/2. If you have a particle with a spin of 2, you have to move it halfway. You have to spin it half a revolution before it looks the same. If you have a particle with a spin of 1, you have to spin it once before it looks the same, which is, usually how most things in the real world work. But here's the weird and odd thing. Some particles, a lot of particles, have a spin of 1/2, which means you have to spin them twice before they look the same. Which, doesn't really make sense, but then again, as Neil deGrasse Tyson once said, the universe is under no obligation to make sense to you. So, quite a profound quote. Because it isn't. So anywho, back to the Standard Model. We have leptons. Now, leptons are the second major group of particles, and they consist of the electron, which we're all basically familiar with from middle school chemistry and science. They are the things that whiz about the nuclei of the atom. So then you have the muon, which is a high energy particle. A lot of them are emitted from the sun. And the tau, which is another particle. And then you have something you might have heard of, neutrinos. Neutrinos are also high energy particles that are also emitted from the sun, and in fact, billions of them are passing through the area of your fingernail, passing through your body every second. You see, they're high energy. Some particles are so high energy that they can pass right through your body, and that's actually what causes things like sunburn. You see, or cancer. You see, when the particles of such high energies hit your body, sometimes they smash right through your DNA strands, and they can rip right through them, and your DNA is broken at that point, or mutations are caused with the RNA, having a misread of, say, a certain codon or something. Anywho. There are 3 types of neutrinos, which are the electron neutrino, muon neutrino, and tau neutrino, because they each obviously are associated with that other lepton. And then finally you have the bosons. Now the bosons are incredibly important because the bosons, there's actually 2 types of bosons, scalar bosons and gauge bosons. Scalar bosons are, we know of one, which is the Higgs boson, which, if you were into this back in 2012, you would know that we found the Higgs boson with the Large Hadron Collider, or at least confirmed it. Now, the Higgs boson, we say, gives particles mass, which is sort of iffy. Basically, what happens is each of these particles has what's called a field. You can imagine these fields as, say, a pool of water. Now, these pools of water are the fields. And say you drop a rock into one of them. That creates what's called an excitation in the field. That's just the ripple, that you see. But sometimes if you drop a big enough rock into them, you see how the water sometimes pops up. There's a drop of water that if it hits enough with enough force, a drop of water comes back up out of the pond, and then obviously, comes back down into it. What's that is what happens when a particle is created, an excitation in the field that excites the field enough to create a new particle, and the new particle flies off into space, does whatever, And basically that happens for really any of these particles. So basically what happens is particles interact with the Higgs field. If they interact more with the Higgs field, they gain more mass, or they have more mass. If they interact less with the Higgs field, they do not have as much mass. That's why in the special relativity video, I stated that even though the photon has no mass, it can't gain relativistic mass, because no matter what, it does not interact with the Higgs field. And even though relativistic mass isn't actually real mass, it's just observed mass. But no matter what, since the photon, which is light, massless, does not interact with the Higgs field at all, it just passes right through it, it has no mass. So, and particles that interact more with the Higgs field have more mass, and vice versa, obviously. So anywho, then we get to what are called the gauge bosons. And the gauge bosons have a very, very important role. There are 4 fundamental forces of nature that we know of. There is the weak nuclear force, the strong nuclear force, the electromagnetic force, and gravity. Everybody knows gravity. That's the big one of the bunch, it's gravity, Gravity is, nearly perfectly defined through Einstein's general relativity, which is different than special relativity. Don't get those two mixed up. General relativity is relativity on a large scale. Special relativity only happens in some cases with flat space-time. But general relativity is if you ever seen the experiment where, the ball is in the, fabric, that's general relativity. Basically, space-time, he showed that space and time are just aspects of the same, you could think of it as a meshwork of reality. And anything in space-time has, anything that has mass will bend space-time around it, causing gravity. And because it bends space-time around it, things will fall towards it in the mesh. So if you have, say, a water bed and you put a bowling ball in it, and you put like a ping pong ball next to it, the ping pong ball is going to fall towards the bowling ball since it's curving the water bed towards it. And that's sort of a good intuitive idea of how space-time and interactions with mass in space-time work, or at least for starters. Anywho, the gauge bosons all sort of not control, but carry. Yes, they're called carriers. They carry one of the 4 fundamental forces. As I said, the 4 fundamental forces are weak nuclear force, strong nuclear force, electromagnetism, and gravity. So the weak nuclear force is carried by both the Z boson, which is Z negative and Z positive, and then the W boson, which is neutral. And what the weak nuclear force controls is basically the one that doesn't interact or don't really see much in the daily life, or don't really care much about in daily life unless, you're a particle physicist. It controls radioactive decay. Basically, yeah, that's the main thing it controls is radioactive decay. At least that's the main thing lots of people know about that it does control. Second, and then you have the strong nuclear force, which is carried by what is called the gluon. The strong nuclear force is what holds the quarks together to create those baryons, mesons, and pions, and all that other stuff. And so it's called the gluon because it glues them together. And then you have electromagnetism. Now, electromagnetism is electricity and magnetism. They're just the same. Think of it 2 sides of the same coin. They're the same force, but just they're just different ways of showing it. Now, the electromagnetic force, you might be surprised, is actually carried by the photon, which this was how, way back in the 1800s, it was shown that light, electricity, and magnetism were all just the same force, but just different ways of it being, shown in the real world. Different aspects of it. And then finally you have gravity. Now, gravity is the odd one out. Since gravity has already been described by space-time, Einstein's, general relativity, it's hard to say where it fits into the standard model, since the standard model requires all those 4 forces to have a force carrier particle. But there is no force carrier particle for gravity, since gravity is just a product of mass, curving space-time. The problem is that we need a particle for it, which is called the graviton. We already know what it should probably appear like. It should have a spin of 2. It should have 0 mass and 0 charge. But we haven't found it yet because we don't know if it even exists. And the goal of physics, or theoretical physics right now, is to somehow merge general relativity with the standard model in quantum mechanics, because that would create a theory that would describe all of physics in one equation, which means you could quite literally describe anything, any particles interacting with any other particle in any point in space and time, perfectly. You could describe how any particles could, if you know the initial conditions, positions and, spins and all that stuff, and velocities of any particle, you could calculate what would happen. The only problem is that we don't know how to do that so far, because, general relativity works on finite numbers, 1 plus 1 equals 2, 2 plus 2 equals 4, yada, yada, yada. That's the kind of, basic finiteness that we all know. What quantum mechanics does is it works on probability. Quantum mechanics works on probability, and basically it states that if you have a particle, you do not know if that particle is where you think it is. And Heisenberg's uncertainty principle states you can either know its velocity or its position, but you cannot know both. You can, because the closer you get to one of them, the further you don't get to the other. And basically, it works on probability because you know either the particle has a probability of being there, but it also has a probability of being on the other side of the universe, or on the other side of the universe, or, somewhere else. It has a probability of being everywhere, and you only know the 99.99999% probability that it could be there, but you're not certain. You can never be certain. That's the rule of the universe. So this is why physics has sort of shied away. So experiments, you see, for quantum mechanics don't really work because you can't experiment with this stuff. What you do now is called a thought experiment. You think about it in your head. That's what Einstein was doing with, say, his man in the falling elevator, or other such stuff like that. And so, basically, that's sort of the standard model, and it's sort of what I would call the gateway into particle physics, and eventually into quantum mechanics. So, oh, sorry, my finger's there. And so I think that's where I'll end it for now. So see you guys later.